So, now it's time to speak about the thermodynamics of electrochemistry, so the electrochemical thermodynamics. So in general, entering more deeply in the electrochemistry, it's important to know about the existence of, from a physical point of view, the thermodynamics and the kinetic. So the thermodynamics deals with everything concerning the stability. And in general, the final aim of the thermodynamics is to describe the relationship existing between the free energy of a certain reaction made in certain condition as a function of the potential, the electric potential. Whereas, even if it's true that the thermodynamics deal with everything concerning stability, we will see these, for instance, during the development of the Nernst equation and the use of the Nernst equations in the Pourbaix diagram, extremely important both for electrode comparison but also for corrosion characterizations and understand the corrosion process. But the Pourbaix diagrams are even extremely important, for instance, in battery. But if it's true, the thermodynamics is focused on stability, we need also to consider the kinetics. The kinetics describe basically in which way the current is able to affect the potential. What does it mean? That the kinetic, if it's true that thermodynamics deal with this function, the kinetics, it's focused on this function. And so, when we are speaking about thermodynamics, we are considering thinking about battery open circuit condition, but we will see this concept later. Whereas, when we are dealing with kinetic, we need to study in which way trying to speed up the reaction, the electrochemical reactions in a battery can affect, for instance, the final output voltage, in which way the speed of the reactions can change the potential, so the current. The current is the speed, basically, and the potential is the final output. But we will see these concepts in a dedicated lesson. So now let's focus our attention on thermodynamics. So, in order to understand the thermodynamics, in order to understand in which way we can correlate the free energy of a reaction, of an electrochemical reaction, as a function of the electric potential, let's imagine to consider an hypothetical reaction. This reaction, it could be the oxidation of the zinc, so the reaction between oxygen and zinc to give zinc oxide. This reaction in standard condition is associated with a total heat release that is equal to this value. So if we are taking zinc and oxygen and we are mixing zinc and oxygen directly in a calorimeter, what we can appreciate as output value of heat release in standard conditions is something like this. But now let's try to promote this reaction from an electrochemical point of view. So we want obviously to produce this reaction. This is a redox reaction because the oxygen passed from 0 to -2, so we have the reductions of oxygen, and at the same time the zinc it passed from 0 to +2, we have the oxidations of the zinc. So these overall reactions, it could be seen as a sum of these two same reactions. Basically. And so, since this is redox reactions, it can be used even in order to derive electricity in a galvanic cell. In which way? So we can say that we have, for instance, a current collector of chopper here, we have here our electrode of zinc, and maybe here we have some zinc oxide as a product of the reaction. We have the resistance, and here we have a carbon, for instance a graphite support with, also in this case, a copper or aluminum or steel current collector. This is graphite or a carbonous layer. Often we will see this concept speaking about zinc air batteries, for instance, or in general metal air battery, but the point is that we need to have a support that is able to allow the diffusions of oxygen. Obviously, oxygen in this case is taken from the air, and so we need to have a porous electrode that at the same time avoid the drying of the electrolyte, and so it's hydrophobic, for instance. But from the other hand, it's able to allow the penetration and the diffusions of oxygen in the catalytic side in order to promote the semi-reaction of reductions of oxygen in order to achieve the total one. Obviously, we need to have the electrolyte, and in this case, the electrolyte, it could be an alkaline electrolyte, for instance, potassium, in an aqueous system. The galvanic chain, that is basically this graphic scheme that describes all the different components in a cell, is something like this. Current collector, zinc and zinc oxide, the electrolyte, alkaline, in aqueous system. We are in super alkaline conditions. We will see in a specific dedicated lesson what does it mean. And obviously oxygen in a graphite, in a carbon support, and again another current collector. So basically, if we are imagining to close the circuit, maybe this is open, and we can close the circuit, the electrons start to move in this direction. And what is actually happening is that this reaction is proceeding. In the very beginning, we have described these reactions only imagining to mix in a calorimeter the two reagents and obtain the product and obtain the final output it released. In this case, the concept is exactly the same, because we are exploiting redox reactions, but in which we are forcing the pathway of electron in an external circuit, but it's the same thing. What does it mean? That if we want to take the cell, this is the cell, and the circuit with the resistance, and we want to put the entire system in a calorimeter, what is happening is that we are obtaining a final heat release that is exactly the same value previously seen, because it's the same reaction. So if we are taking this entire system and we are putting it inside a calorimeter, we obtain exactly the same result as before. But what happens if we want to separate the cell in one calorimeter and the resistance in another one? So basically, again, the sum of these two contribute is equal to this value. So we have a certain heat release in this calorimeter due to the resistance, and we have a certain heat release from the cell. So basically, we can say that the sum between the heat release from the cell plus the sum of the heat release from the resistance have a value that is exactly the previously seen, regardless the value of the resistance. But the point is that it's true that the sum is always the same regardless of the resistance. But if we are varying the value of the resistance, maybe we are increasing the resistance or we are decreasing the resistance, what happens is that this contribute change with respect to this one. The sum is the same, but maybe this is different and this is different. And especially, if we want to consider an ideal situation, a limit situation, we can imagine that our resistance can go to infinite. when our resistance go to infinite, it means that the reactions proceed so slowly that we can imagine to have the minimum of energy losses. So basically, the energy lost is extremely low. When we are in a condition in which the resistance is infinite, the movement of electron is infinitesimally low. Is basically that is something like that our cell is in an open circuit condition. So basically, if the resistance is infinite, the cell is open, and actually in the reality we're not able to appreciate a real flow of electrons. But this is just a theoretical imagination's condition. Obviously it not make sense to use a resistance that go to infinite, because in this situation the circuit is closed and no current can pass. But if we are, from an asymptotic point of view, imagining to reach this infinite value, we can imagine to observe an infinitesimally slow movement of electrons. So basically this literally means that we are in a condition that is known as thermodynamically reversible condition. So we are in open circuit condition, so open circuit condition, OC. And we are in thermodynamic reversible condition. In this condition, basically, the heat released from the resistance is maximum. So we can say that the limit of QR for R that go to infinite is equal to minus 310 kilojoule. Whereas, in the same condition, the heat released by the cell when the resistance is go to infinite is equal to minus 40 kilojoule per mole of zinc. This is quite obvious. And so what does it mean? That the sum is always again this value, but in this case we have the maximum of heat released due to the resistance and a minimum of heat released due to the cell. And why this is important? Because the only heat that is interesting for us, the only energy is the energy discharged on the resistance. Because the energy discharged on the resistance is connected with what is known as useful work. So the work that is directly connected due to the development of the reactions, and is the work that we can actually use in order to make an action. We have described in one of the first lessons that the resistance is important, because the resistance is that instrument that allows us to use energy, to use electricity in order to make an action. The reaction gives us, the battery allows us to transform chemical energy in electricity, but it's that resistance that is able to collect this electricity and use it in order to promote an action. And so all the heat in general discharged on the resistance is connected with a useful work, because we can use this heat in order to make an action, a light or even a mechanical action. Whereas the heat released from the cell is just simply lost. We aren't able to, in any way, to use this heat in order to promote something, to use this heat for do something. So it's just the entropic contribute that we need to pay to the universe in order to promote this reaction. But this entropic contribute, this energy that is simply lost, is minimum when the reaction is proceeding extremely slowly. And so it's minimum when the resistance is go to infinite. It's minimum when we are in thermodynamics reversible condition. When we are in thermodynamic reversible condition, when the circuit it could be considered as closed, we can say that we have the maximum useful work, because the entropic contribute to pay to the universe is minimum. And so knowing this, and since we have described now that QC so the heat released from the cell is the entropic contribute, so is energy associated with accidental work that is useless. We can say that since this is in heat, and since we are in thermodynamic reversible condition, this literally means that the Clausius equation is valid, and so we can say that this is basically equal to this one. But we know that the value of this is minus, for this specific reaction, 30 kilojoule per mole of zinc. We have this value, that is the total heat released from the reaction. And from the Gibbs-Helmholtz relationship, we can say that this, since it's equal to this, allows us to understand how the maximum useful work, the total energy that we can discharge on the resistance when we are in open circuit condition, is equal to the free energy of our reaction in standard condition. And so this is a first relationship between something that we can use from the cells, a first relationship between the energy released on the resistance due to electrochemical process and the reaction used for that electrochemical process. So we are getting close to solve this function, because now we have an idea about in open circuit conditions, so when the current is actually zero and we are actually looking for a thermodynamic descriptions, avoiding any kinetic concepts, well, we are getting more close to this function. And now what we can do in the next video is finish these topics and try to proceed with the actual real mathematical demonstrations that allow us to pass from this very generic function to a more precise one, that it will be also the starting point, for instance, for the descriptions of the nearest equation.